how to solve a system of linear equations of the form Ax is equal to B, where A is a matrix of dimensions m cross n, x is a vector of dimension n cross 1, while B is a vector of dimensions m cross 1. So it's something like we have m equations, m linear equations, and n variables. Also, what we know from matrix notation is that uh, yeah, from matrix notation is that we can write A in the form of column vectors like this, and writing x in this form, we can write ax in this form and b as a vector. So now if we want to check whether a solution exists or not, it's the problem is simply equivalent to this problem that can be written that can be written as a linear combination of the vectors a1 to an. If b can be written as a linear combination, then we say that the solution exists. A solution exists rather. There might be infinite solutions, there might be more than one solutions, and there might be a single solution. So if B can be written as a linear combination of a1 to an these vectors, then we say that a solution exists. If B cannot be written, then no solution exists. This is simple enough and intuitive enough. Uh, this is what I've written here. If B can be written as a linear combination of a1 to n, that is if B is an element of the span of a1 to n, or another name for this, since a1 to n are the columns of the matrix A, if B is a, we can equivalently say that B is element of call span of A. Now, assuming we have already checked the condition number 1, we move on to checking the condition number 2, that is the uniqueness of solution. So once we have concluded that a solution exists, we need to find whether uh, a single solution exists, that is whether the solution is unique, or whether multiple solutions exist. And we can conclude that if multiple solutions exist, that implies that infinite solutions exist, because of the way linear combination works, that if x1 is a solution and x2 is a solution, then x1 alpha x1 plus beta x2 would also be a solution, and this gives us infinite solutions. So yeah, that's there. So we already checked existence in point number 1. Now, from the fundamental theorem in linear algebra, we can say that a1 x1 plus up to an xn is equal to b. Now the solution is given by x vector. The solution is unique if and only if the vectors a1 to ai are linearly independent. Assuming we know this fact, we can say that all the set of vectors a1 to an must be linearly independent. That is equivalent to saying that a1 to an must form a basis of the call span of the span of a1 to an. This can be concluded, and yeah. So if so, in conclusion, if a1 a2 up to n these are linearly independent vectors, then we can say that the solution would be unique. Now, equivalently arguing from the side of augmented matrix, matrix, we can also kind of make some formulae which is of the form that, so consider the augmented matrix of the form A B, where the matrix A would be written in this form, B would be written in this form. They both would be concatenated to form a single matrix known as the augmented matrix. This is A, this is the vector B. Okay, so if rank of A is equal to rank of A, the augmented matrix A conjugated with B, if both of these ranks are same, what this basically implies is that, okay, what is rank? Rank is the number of linearly independent columns in the matrix. So if rank of A is equal to rank of A is equal to rank of this matrix, this automatically implies that B can be written as a linear combination of these vectors. And from what we discussed above, this means that a solution definitely exists. Now, assuming this condition is true, we form two subcases, A and B, where A says that if rank of A is less than n. If rank of A is less than n, what this means is that the number of linearly independent columns from A1 to An is less than n, which implies that A1 to An, these columns are not linearly independent. And from the discussion we had above, this implies that infinite solutions exist. If rank of A is equal to n, then all the columns of A1, all the columns A1 to An are linearly independent, and hence a unique solution exists. Now comes the second case where rank of A uh, is not equal to rank of A conjugated B. This means that either it can be greater than or it can be less than. Now it's very intuitive that the inequality sign cannot be greater than equal to, because rank of a matrix is defined as the number of linearly independent columns. So it is obvious that the number of linearly independent columns cannot be greater than the number of columns itself. So this is not a valid inequality. We'll consider this inequality here. Okay. So if the rank of A is less than rank of A conjugate B, this means that A conjugate B has more number of linearly independent columns compared to A, which is equivalent to saying that B cannot be written as a linear combination of A1 to N, which automatically uh, implies that no solution exists. So this was a discussion on the solution of the linear system of equations.